Welcome everyone to the talk, Going Deeper Than Tracking Using AI to Recognize Emotional States and Pain in Animal. Professor Anna Zamansky is an associate professor at the Information Systems Department of the University of Haifa. She leads the Tech4Animals Lab, which develops AI solutions for understanding animal behavior and improving their health, well-being, and welfare. Anna is a computer scientist holding a master's degree from the Technion and PhD in mathematical logic from Tel Aviv University. She was a Marie Curie postdoctoral fellow at the Technical University of Vienna, Austria, prior to starting her lab devoted to the use of AI for animals. Please, everyone online and in person, let's give a warm welcome to Anna Zamansky.
Thank you. It's an honor and a pleasure to be speaking to you today. I find it really inspiring and fruitful to network with this wonderful community, and I wish I were there in person with you. And thank you to the wonderful organizers for this great event. So nice to meet you. We are Tech4Animals. We are a lab at the University of Haifa. We are a multidisciplinary team, and we study AI applications for promoting animal welfare, health, and well-being. Our main focus is developing AI models that decipher and recognize pain and emotions, internal states in animals. We mainly work with the visual modality, such as the body language or facial expressions, but we also look at other modalities, vocalizations, sensor data, and so on. Nowadays, there is an increasing number of researchers studying animal behavior using AI. And it is really amazing. I think that our unique perspective is that we are actually very interested in the perspective of the machine. We ask the question, how does the machine see pain and emotions? What can we learn from the way it sees it? Is it different from the way that human experts look at behavior? And what is the holistic process that will allow us to work together with AI to better understand animals? So let us dive right into the question of our tool, which is, can AI recognize emotions and pain in animals? I hope you will discover by the end of the talk that the answer is complicated, but actually encouraging. But first, we could maybe ask with a simpler question. Can you recognize emotions and pain in your dog or cat? Well, probably most of you will tell me, well, that's funny. I don't need AI to tell me how my dog is feeling. I see that it's happy to see me or that my cat is in stress. But actually, you should be careful when making this statement. Let me ask you another question. How would you describe your cat? Would you say, my cat is my pet, companion, friend, or a furry baby? So the more attached to the animal you are, and the more humanizing you are, the less chances you have to actually recognize behaviors correctly. So there has been a study which has shown that people who have humanized in their description their cat, calling it a child or a family member or their best friend, actually were less successful in correctly recognizing emotional states of animals. So our love for our pets and our connection and attachment actually makes us sometimes assign very complex social emotions, such as jealousy, compassion, for which we do not yet have scientific evidence. And we are not so correct at recognizing these states. And what about dog bites? This is of increasing concern. And actually, studies show that most of the dog bites occur in familiar homes with familiar dogs. It means that dog owners really fail to recognize emotional states which lead to dog bites and aggression. So maybe, and what about farm animals where the farmer has hundreds or thousands farm animals? It is very hard to monitor their emotional state, their stress and pain, and so on. So it's even more difficult for farmers who deal with many different animals, and it's hard to individually think of each one of them. So maybe it is not so easy for us to recognize emotions and pain as we first think. And how about science? What is the status of scientists in recognizing emotions, pain in animals? So actually, this very simple question, do animals feel emotions, has been debated for decades by philosophers and scientists. But now we are finally at a stage where studying animal emotion is widely accepted in the scientific community. And we understand that emotions help animals to make decisions about how to respond to certain situations. And for group living animals, having emotions is fundamental to forming packs and relationships. We also understand that emotions are closely related to animal welfare, and there is a need to depart from just not having negative emotions and stress towards having positive emotions, especially in farm animals. And finally, we also know that facial expressions are a very important channel for communication of emotional states in humans and animals. So how do scientists actually objectively measure these facial behaviors? Well, that goes back to the psychologist, Paul Ekman, who introduced this facial action coding system. This system is anatomically based, and it actually allows us to code facial expressions by breaking them into individual components, which are called action units. And luckily for us, working in the field of animal emotions, these systems have been recently extended to many non-human animals, including horses, cats, dogs, and many types of primates. So we can use animal facts to objectively measure and quantify facial behaviors. Let me show you some examples of how researchers are using this system. It should be noted that in order to code using animal facts, you need to be a certified coder. You need to do a long certification process. And actually identifying action items is really very difficult because they are very subtle. So this is the first of its kind study performed by my colleague, Annika Bremhurst, in her PhD. She did a control experiment with 30 Labrador retrievers. So she picked one breed, focusing on the subtle facial expressions the dog performed in emotional states of positive and negative balance. She induced these states using toys and food. And then she coded using DogFACS these facial expressions. And she discovered that some action units are typical for the positive condition, such as the ears adductor, where the ears go out, while some of them are more typical for the negative emotions, such as blinking, nose leak, ear flattener, so the ears moving down, and so on. So here you can see how complicated it is to actually use DogFACS coding. It took her 1 year to collect this data and 1 more year to code it just to reach these scientific discoveries. Another example comes from another colleague of mine, Brittany Slotkiewicz. She actually published a study this year that went completely viral. She discovered by studying social interactions between cats in a cat cafe in LA that cats have nearly 300 facial expressions, and some of them are different for positive interactions, and some are more typical for negative interactions. So again, she collected hours of video footage in this cat cafe, and you can see how hard it is to see these subtle expressions because the data is so noisy and you cannot see all the cats well. And she coded CatchFacts to discover so many different expressions. This was very surprising for scientists, that cats are so expressive in their faces when connecting to conspecifics. So it took her 1 year to code this data. So it is a laborious effort to come to these discoveries concerning facial expressions when we speak about emotions. And what about pain? This is a patient in a veterinary hospital. This cat is suffering from pain. And vets need to have very practical instruments in order to assess pain in their patients, right? So they use behavioral changes, body postures, and facial expressions. So it's important to have scales which are practical, which can be done in clinical settings and to receive results fast. for instance, to make decision on when to administer analgesic treatment, when to give painkillers to the patient. So these instruments really need to undergo rigorous validation before they are used in clinical practice. So, for instance, for cats, there are only 3 validated scales for pain assessment. 2 of them use behavior, and 1 of them, the Felin-Grimes scale, uses facial expressions. So just to show you an example of how a behavioral scoring would look like, so you would ask the vet to look at the cat, to observe the cat in its cage, and you would ask questions about its behavior. So first of all, it takes time to observe the cat. It is time consuming. Secondly, a physical presence of the vet near the cat actually induces stress, and stress looks in cats very much like pain. So it is really the holy grail to distinguish between the two. So there are some disadvantages in using behavioral scales. An attractive alternative are the Grimes scales. So here we see a bit of the Felin-Grimes scale, which looks at the muzzle tension. The benefit of this is it's really easy to use, and the vet can do it just by looking at photographs. They don't really need to be physically near the cat. But still, you can see that these things are not exactly objective. For instance, looking at these cats, how would you assess their muzzle tension? Now, the cat on the right has an Elizabethan color, which actually hints that it is the most painful one. But you can see it's very difficult when looking at real cat patients to decide whether the score is 0, 1, or 2. And there is a degree of subjectivity in assessing pain, even using the Grimes scales, which are validated instruments. But don't forget, they are validated for specific types of pain, for instance, working only on acute pain, and they are not so relevant in chronic pain. And also, studies have shown that there are biases related to experience. So less experienced vets usually score higher, and even to gender. So female vets score higher than male vets, having more empathy towards painful cats. So this is really not very easy to assess pain in animals. Scientists seem to have objective tools, but their use has many challenges. It is laborious. Manual coding, it requires special expertise. In order to get animal facts coder, you need to really learn and undergo a certification exam. There is subjectivity, bias, human error, and so on. So these are the challenges that scientists are facing today when studying emotions and pain. And then, of course, this leads us to the question of our talk. Can AI help? Of course, the good news are it is already doing that in the human domain. It is actually revolutionizing the way we study emotions and pain in humans. Affective computing is a really mature field of research, and there are many commercial tools such as Noldus Face Reader, Affectiva for emotions, and Paycheck, which is an app that is being used in clinical settings for nonverbal patients, infants, and patients with dementia. So this is already working amazingly great in the human domain, but we are here to speak about animals, and the transition from humans to animals is not at all trivial. That is what I would like to show you, the reasons why. And we are making our baby steps in this direction. But first, the elephant in the room. You would probably say, well, ChatGPT and large language models and large vision models are so great at everything today that they probably will be able to recognize emotions and pain in animals. There is even a famous story about the ChatGPT, which saved a dog's life. So this border collie was bitten by a very rare tick, and the vet missed it, and the dog was actually about to die. And its owner gave the test results, the blood test, to ChatGPT, and it came up with this diagnosis, which the vet said, wow, I did not think about it. So yeah, ChatGPT saved this dog's life, but it doesn't mean it can replace human vets, or that it even understands the diagnosis that it produced. So what about emotion recognition? This is DALL. DALL 2, 1 year ago, producing images of cats in pain. Well, this is not exactly like the grimace scale that we have just seen, which describes how pain in cats looks, right? This is an anthropomorphic version of pain, which looks more like humans screaming. And if you ask ChatGPT today to produce images of painful cats, it will refuse to do so. But there is still a trend of taking images of animals and trying to use ChatGPT and large vision models, which use zero-shot and unsupervised approaches to classify emotional states. So there are papers and they report quite good results, but actually doesn't really work. We have tested it and we have seen that there is this dog for which the model produces the classification of a sad dog. Once we cut the background and put this dog on a cheerful green grass, the model changes its mind and says the dog is happy. So these models do not look at the facial expressions or body postures of the animals. They look at the context, at the things surrounding the animal. So ChatGPT does not have a chance to actually accurately recognize emotional state. Just because in the data it has been trained on, there was no quality data related to pain and emotions in animals, because it is very hard to produce such data. So still, we believe for now, at least for the foreseeable future, that supervised learning is the way to go if we want to scientifically approach the problem of recognition of emotion and pain in animals. So just to remind you how supervised learning works, suppose I want to teach my model to separate between dogs and cats. So what I will do, I will show it examples of cat faces and dog faces, and then I will let the machine pick on the features separating dogs from cats. So what is the feature? For instance, the feature of color would probably not be a good feature because both cats and dogs may have the same color. What would be a good feature? Maybe some proportion between the ear and the head, or some more complex combination of a number of things. So we could decide on the features that we want to use for this classification, or we can let the machine discover them by itself. And that is exactly what deep learning models do, right? They learn features from data using architectures of neural networks, which simulate the way our brains learn new concepts. But so their performance is great, and they would probably very quickly separate dogs from cats. But it comes with the price. The price is that the decision processes of these networks are so complicated that we basically call them black box because we don't understand them. So in order to open the black box, we study explainability. We're trying to understand why the deep learning network makes these decisions. And it's important if we want to use our models in clinical settings or in welfare settings. It's important that the users understand why these decisions were made. But let's go back. Our question is not about whether it's a cat or a dog that have a strong, medium, or no pain, or what type of pain, is it chronic or acute? And if we speak about emotions, whether the emotions are positive or negative valence, or maybe specific emotions such as positive anticipation or negative frustration. These are very, very subtle classification tasks. They are much, much farther than just deciding whether we have dogs or cats. And then we come to one huge problem that we have in this field. Where do the labels of the data come from? Of course, dog versus cat is really easy. Anyone can do it, right? But how do we know if the cat is in pain or not? Or how do we know that this dog is experiencing positive or negative emotion? How do we know what is the ground truth? And here we come to these huge problems which are not necessarily there for the human domain. One of them is that the most commonly used method in pain research and in emotion research for humans is self-reporting. But animals cannot tell us how they feel, and they cannot verbalize the degree of their pain. So one big difference is that we have non-verbal individuals which cannot provide information about their internal states. Another thing which is different in the human domain, a lot of huge quality data sets of emotions are actually produced using actors. We cannot ask the dog to do a happy face, right? Or a sad face. So this is another gap for humans. We can do actor databases, and that is why we have huge data sets and models that have been trained on them, but animals don't do that, right? So what options do we actually have? So we do have the possibility of using expert scoring or expert consensus, like consulting several experts. But is it not a kind of a vicious circle, because we wanted to use AI to get away from subjectivity and human bias? But by using expert scoring, this penetrates their labeling, right? So all we could teach the AI in this way is to imitate the way that human experts think. And this is a kind of looking under the light and not necessarily a good solution. In some cases, we do use expert scoring. We care a lot about reliability. We care a lot about using multiple scorers and measuring the agreement between them to make sure that we trust our labels. But this is really one important issue. But the best way for us to label data is to either have time points. So for instance, a cat before surgery, so we know it's not in pain, and a cat after surgery. Of course, this surgery is planned, and these cats are patients in a hospital in Germany. So the pain is not called to the cats in any way to study this, but we actually need to plan our data collection in a way that we know that these time points reflect the ground truth. Or control experiments. So for instance, here we have a dog hearing a scary noise versus a dog hearing a good whistle. So this is a positive anticipation, which is induced experimentally. So when we induce the emotional state, then we trust more the labels of our data. So these are huge issues which are not present in the human domain, and we deal with them all the time. So suppose we do have a good data set with good labels that we can trust. Now what? What is our next step? So here we need to make a lot of different decisions. Do we go for deep learning architecture, which usually would give us good performance, but these approaches are data hungry? So if we have a small data set, we would not go in that direction. If the data is extremely noisy, for instance, the cat cafe data where the cats were photographed in a cat cafe in a real naturalistic setting, then maybe the faces are not clearly seen. Maybe we are not able to actually follow these faces and see how they change in time and have the temporal dimension. Maybe we will just extract simple frames and work with them. If we have multiple animals in the frame, we need to know who is who. So we have a lot of pre-processing to do, both manual and automated. So the really hard technical work is just beginning at this point. Now, as I said, we know from experience that deep learning approaches perform really great for these types of tasks. But then we really should care about explaining the reasoning of these approaches because, as you probably know, they are known to have bias. Yeah, they can see sometimes clues on the image which are not really related to the facial expression or body posture. For instance, if happy dogs were photographed at 5 o'clock and sad dogs at 6 o'clock, then maybe the model just looks at the time and it has 100% accuracy. So we need to make sure that these bias are not introduced into the network's decisions. So in our lab, we are exploring a lot of different methods of how we can explain the reasoning of deep learning networks. Here you can see using visual explainability techniques, such as showing you a heat map of the areas of interest, the pixels that the network found the most informative. So by using this in a systematic way, we have been able to discover then that for the task of pain, machine always is more interested in the eyes than the ears. It is consistent across species. We saw it in horses, in dogs, in cats, and it is completely counterintuitive to human vets who say that for cats, they always look at the ears, as well for the horses. So this is an indication that the machine sees things differently from human experts. So how can we learn from it? How can we combine these two approaches? We also try to map two-dimensional heat maps to 3D models and seeing where on the animal's head the network is focusing. And here you can see this rabbit. You can see a temporal dimension and the confidence level of the network is changing. And here, for instance, in the rabbit, the posture seems to be consistently most informative because that is where the network is looking for most of the time. So these are just examples of things that we can do to peek into this black box. Another type of explainability can be provided if we go back and remember what the approaches in the human domain are using. They are using facial landmarks, which actually reflect the movement of the muscles of the face in an explainable way. Actually, platforms such as Deep Lab Cats, probably many of you have heard about them. Actually, they have unlocked the potential of animal motion tracking by providing this flexible framework in which we can train deep learning models to recognize key points on any body of any type of species. So this has really unleashed the potential of automated behavior analysis. And there are also other platforms like this. But we have discovered that these existing platforms are not flexible enough for capturing the very subtle facial changes related to emotions and pain. And so we have developed our own architecture called the ELD, which is a multi-animal, multi-breed landmark detection model. And the idea is that the face of the animal is mostly rigid and not moving, not like the body, which is moving a lot. And so this detector actually treats each facial part differently. So the ears, the eyes, the muzzle, and it is species specific. And another thing which is species specific is the placement of these landmarks. So for instance, for cats, we have 48 landmarks. For the dogs, we have 46 landmarks. And they are grounded in the anatomical structure of the animal. They are grounded in CatFACS and DogFACS. So these are already some quite good performance of our automated detector. We have already have it open for the community to use for cats and dogs. And we are currently developing it for horses and different types of primates. So you can actually find this platform on our website, and you can use it for facial analysis of dogs and cats. And of course, now we understand much better how to extend it to any species. And for a new species, we would typically start by talking to an expert who could tell us what are the facial landmarks that are of importance for that particular species. So making this analysis species specific is important because pain and emotions, they may have the similar mechanisms, but they look differently on the muscles of the animal. And what I find the most exciting about this approach is that we are able to produce a facial signal which is continuous, which is not like any traditional approaches which are usually used in ethology. The coding of behavior is usually discrete. Here we have a continuous signal which allows us to see facial behavior over video in a temporal dimension. So just to show you some examples of what we can do with this type of facial analysis, revisiting the chemical fence study, we have been able to run this detector. As you can see here, this is very noisy data, and the detector is losing the face a lot. But still, we were able to establish that in addition to the 300 different facial expressions that the cats are doing, they are also doing facial mimicry, which was very surprising. We did not know that about cats. So cats do not only produce many different expressions, but they mimic the expressions of others. And they do it more in affiliative, positive interactions. That's really interesting. We did not know that for cats. And using this computational approach makes it possible. Another thing which we have been able to discover is comparing the facial behavior of a brachycephalic breed, the flat-faced dogs, as opposed to normal-cephalic dogs, like terriers and so on. So there is this hypothesis that due to the facial muscles on the faces of the flat-faced dogs, they are not as expressive as the other types of breeds. And so far, this type of studies have only looked at perceptions of humans. So we would ask humans, okay, look at this dog, does it seem sad or happy? And look at this brachycephalic dog. But now we are actually able to quantify the facial dynamics directly. And indeed, we see that in the same emotional situations, which are induced in a controlled way, for instance, the owner leaving the room, so this is a negative situation, or the dog is shown some food, so it is positive anticipation. And we can really see that brachycephalic dogs have less dynamic movements in their faces. This is really a very fascinating result for me. And finally, my personal dream is to have, like Noldut have the face reader for people, we would like to have the dog face reader for dogs. We are not there yet because we need a lot of good data from many different breeds to do that. But we are able to computer assist DogFACS coding, and we have reduced the time it takes to code DogFACS coding by almost 1/3. So we look at the areas, we can highlight the areas where there is some interesting facial behavior, sending the codec to those segments and cutting the segments which are not interesting. So this is one step towards actually having a good dog reader. And of course, we have seen the patient app for infants and nonverbal patients. And now we do the same for cats. So cat pain detection using landmarks. And of course, we can also use conversational AI and LLMs to explain what the model sees, to provide some advice, and so on. So another question, which is maybe interesting to discuss before we end this talk, is, AI can recognize emotions and pain in animals. I have just shown you some very nice results. Can it do it better than human experts? Well, this is a tricky question, because for answering such a question, I would need to have a very good data set on which we have both the scoring of the human experts and the ground truth, which is established in some other independent way. So we have been lucky to obtain such a data set for sheep pain. Now, sheep are very interesting animals because in them, the pain is mostly expressed by the tightening of the muscle underneath their face here. So actually, the side view of the sheep is more informative than the front in terms of pain assessment. So the human experts and the machine were shown exactly the same visual information, 2 photos, frontal and side of the sheep. And now we have been able to finally show that the machine outperforms human experts when looking at exactly the same visual information. So another interesting study I wanted to mention, although it's not related to facial expressions, but here again, a machine outperforms many working dogs experts in telling when the dog is sniffing the target smell. So this is a dog doing a training. It is trained to alert on a specific type of smell. This type of dogs are used for detection of drugs, cancer, explosives, and many other materials. So having errors in this is really expensive. So as you can see, there are anecdotal evidence that usually experienced dog handler can look at the dog and 1 millisecond before it starts alerting, they already know it. And they say it's mostly because of the tail. So in this study, we have looked at the tail behavior. And again, we are proud to report that the machine beats dog experts here as well. And this is just the beginning. The more data sets we have, the more competitions we can do. How do the human vets and the human dog handlers feel when they hear these results? Well, I think maybe Garry Kasparov was beaten by Deep Blue in 1997, and he felt like his world is falling apart. And at that point, everyone thought this is the end of chess. But that's not what happened, right? Today, any chess champion has an AI coach that enhances their capabilities. So we believe the same will happen to the human vets and to the human dog handlers and to any professional that works with animals and wants to understand their behavior. So just to finish, I wanted to say, I hope I have given you a feeling of the kind of problems we are dealing with in our field and working in a multidisciplinary area and the need for collaborating with experts who have a different terminology and they speak a different language. It's not always easy and sometimes frustrating, but also fascinating. Also, the problem of space in the field of AI. Things are changing so quickly, but animal behavior science is very conservative. And so just bridging this problem of space is really a challenge for us working in this field. And of course, the main big thing is having good data. If we have good data, we will be able to be more like the human domain, where AI is already revolutionizing everything. So this is why we are extremely thrilled to talk to any experts, any people working in the field, because you are sitting on a gold mine of data that can be so useful to us. And please feel free to get in touch with us and tell us about any problem that you would like to solve. And we would love to see if we have the tools to help you. So thank you so much.